Hello there and welcome to the Sleepy Professor. I'm really glad you found your way here tonight. Maybe you've had one of those long, exhausting days where your mind just won't stop spinning. Or maybe you're the kind of person who loves falling asleep to fascinating thoughts about the cosmos instead of counting endless sheep. Whatever brought you here, this journey is made just for you. You don't have anything to do right now except rest. Let your mind start to relax. Feel your breathing slow down naturally. Notice how your body begins to grow lighter, as if gravity itself has decided to be a little gentler with you tonight. Because we're not just going to stargaze together. We're going to drift through our home, the Milky Way Galaxy. This vast spiral of hundreds of billions of stars, clouds of dust, and mysterious dark matter has been turning slowly through space for over 13 billion years. But beneath all that beauty, beneath that peaceful glow you see on clear nights, there are secrets. There are rogue stars racing away at impossible speeds. There are invisible forces holding everything together. There are ancient stellar remains that challenge everything we thought we understood about how galaxies form and evolve. Tonight, we'll travel gently from the sweeping spiral arms all the way to the secretive, hidden core. We'll encounter colossal collisions between galaxies, discover stellar nurseries where new suns are being born right now, and explore the strange, unfinished story of a galaxy that's still growing, still changing, still becoming something new. Some of what you hear tonight might surprise you. Some of it might spark a quiet curiosity as you drift towards sleep. And hey, just before we begin our journey, if these calm, curious explorations help you unwind at the end of your day, consider hitting that like button and subscribing to the channel. It really does help others find their way here too, one sleepy soul at a time. Now let's begin our gentle drift through the stars. When galaxies collide, the Milky Way has already collided with other galaxies, and it's going to happen again. Our galaxy might feel like this stable, unchanging home, but the truth is, it's actually built from the wreckage of others. Over billions of years, the Milky Way has absorbed smaller galaxies, drawing them in with its powerful gravity, slowly unraveling them, and scattering their stars into long, delicate streams that wrap around our galactic disk like ghostly ribbons. One galaxy in particular, the Sagittarius Dwarf Galaxy, is being pulled apart by our Milky Way right now as we speak. Its stars are being slowly stolen, stretched into long tidal streams. And far off in the night sky, the great Andromeda Galaxy is drifting slowly but steadily closer to us. In about 4.5 billion years, these two great spirals will merge in what astronomers call a cosmic collision. Now, stars will almost never actually hit each other because space is so incredibly vast. But the shapes of both galaxies will change forever, folding and warping into a new form, something vast and quiet and different. Even galaxies you see are not eternal. They evolve, they collide, they end and begin again, transformed by time and gravity. Stars older than home. Here's something that might bend your mind a little. Some stars in the Milky Way are actually older than the Milky Way itself. Not every star you see when you look up was born here in our galaxy. There are these ancient stars called halo stars, metal poor and wandering in long, tilted orbits high above and below the main disk. Astronomers believe these stars may have formed in smaller primordial galaxies that merged with our own billions of years ago, back when the universe was still young and wild. The chemical fingerprints tell a story. They show almost no heavy elements like iron or carbon, which suggests they were born shortly after the Big Bang, before generations of dying stars had a chance to enrich space with those heavier atoms. These stars move slowly and quietly, high above the galactic plane, like elder spirits from a time before spirals even existed, before there was any galactic order at all. When we study their light, we're seeing echoes of a universe that was younger, stranger, and still learning how to become what it is today. A journey through space. Our entire solar system orbits the center of the Milky Way at over 828,000 kilometers per hour. Just think about that for a moment. That's more than 230 kilometers every single second. And even at that incredible speed, it takes about 225 million years to complete just one loop around the galaxy. Astronomers call this path a galactic year. In Earth time, we've only gone around the Milky Way about 20 times since our solar system first formed. When the first dinosaurs appeared on Earth, we were in a completely different part of the galaxy. The stars we see today in our night sky weren't always nearby, and they won't always remain where they are. Everything is in motion, quietly, slowly, endlessly moving through space. Even as you lie here drifting towards sleep, the Earth is turning, the Moon is circling. And our entire solar system sweeps forward through a galaxy that never stops moving. A galaxy still growing. The Milky Way is ancient, but it isn't finished. Even now, at this very moment, it continues to gather material. Gas flows in from the intergalactic medium, that thin cosmic soup between galaxies. Stars arrive from captured dwarf galaxies. Streams of dark matter feed its enormous halo. The galaxy grows not like a living thing exactly, but like a gravitational structure that deepens and evolves over time. Some of this growth happens quietly, through slow infall of gas clouds. Other times it comes with real disruption, as satellite galaxies are torn completely apart and their stars scattered across the sky like cosmic confetti. The galaxy you live in today is genuinely not the same one the dinosaurs saw, and the galaxy your distant descendants might know could be even larger still, stitched together from the ruins of 1,000 smaller worlds. The mystery of the spiral arms. We don't actually know for certain how many arms the Milky Way has. I know that seems like something we should definitely know, right? How many spiral arms extend from the center of our own galaxy? But from our position deep inside the disk, it's incredibly hard to see the whole structure clearly. Thick dust clouds obscure distant regions. Stars blur together into hazy bands of light. For decades, astronomers believed there were 4 major spiral arms, but more recent observations have suggested maybe there are fewer. Or maybe the arms twist and split in ways that are far more complex than we initially expected. Some arms seem to fade into fragments. Others wrap around in unexpected directions. The Milky Way might not be a neat pinwheel shape at all. It could be a living, layered swirl of stars, shaped by gravitational forces we still don't fully understand. Rogue stars flung into the dark. Most stars drift calmly through the galaxy on stable, predictable orbits, but a rare few are flung outward at absolutely astonishing speeds, fast enough to escape the Milky Way entirely and never return. These are called hypervelocity stars, and they're some of the most dramatic stellar objects we know of. Some of these rogue stars are the remnants of binary star systems that got too close to the supermassive black hole at the center of our galaxy. One star falls inward and vanishes beyond the black hole's event horizon. The other gets violently slingshot outward, hurled into the darkness at over 1 million kilometers per hour. These stars travel completely alone, far from the galactic plane, like glowing comets with no possibility of return. They remind us that even in a galaxy held together by gravity, there are moments of violent release, quiet expulsions that send stars flying into the intergalactic night. The Andromeda collision. High above the horizon on autumn nights, the Andromeda Galaxy appears as a faint, fuzzy blur to the naked eye. It's a spiral galaxy much like our own, lying over 2 million light-years away, and yet it's moving steadily toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide in one of the most spectacular cosmic events imaginable. Now, it won't be violent in the way you might be picturing. Individual stars are spaced far too far apart to actually crash into each other directly, but the gravity of both galaxies will warp them into long, stretching arcs. Tidal tails will curl gracefully outward into space. The supermassive black holes at the center of each galaxy may spiral together in a gravitational dance. And after billions of years of this cosmic ballet, the two galaxies will finally merge into a single, larger system. It will be a slow, elegant dance, the future of our home written across the stars themselves. Stars that orbit backward. Most stars in the Milky Way orbit the galactic center in roughly the same general direction, following the overall rotation of the galaxy. But not all stars follow these rules. Some stars, especially in the outer halo, move in what's called retrograde motion. They orbit in the opposite direction to the galaxy's main rotation. These backward-moving stars likely arrived here from somewhere else. They were probably born in dwarf galaxies that were later absorbed into the Milky Way. Their reversed motion is like a quiet signature of their foreign origin, a clue written in movement. It's as if the galaxy carries old memories in the motion of its stars, preserving stories of ancient mergers and cosmic encounters not in light, but in the slow, patient turning of stars against the stream. A galaxy built from consumption. Over billions of years, the Milky Way hasn't grown alone. It has consumed. Small galaxies, faint luminous companions, have drifted too close, been caught in its gravitational pull, and slowly dismantled piece by piece. Their stars are now part of our halo, our disk, or long stellar streams that wrap around us. Astronomers have identified several of these ancient mergers by carefully analyzing the motion and chemical composition of stars. One especially large event, called the Gaia-Enceladus merger, added a huge number of stars to our galaxy and may have completely reshaped the early structure of the Milky Way. Our galaxy is not some pristine, untouched spiral. It's a composite, a patchwork built from quiet collisions, stitched together from the remains of many smaller worlds that no longer exist. Chemical fingerprints in starlight. Every star carries a unique chemical fingerprint, a distinct pattern of elements that was imprinted at the moment of its birth. By studying these signatures in starlight, astronomers can actually trace a star's history, like reading an ancient biography written in atoms. Some stars are rich in heavy elements like iron, nickel, and calcium. This suggests they formed in dense, metal-rich regions where previous generations of stars had already lived and died, enriching the environment. Other stars are almost pure hydrogen and helium, indicating they were born when the universe was still very young, before much stellar processing had occurred. These differences allow scientists to group stars into families, uncover ancient galactic mergers, and reconstruct the hidden story of how the Milky Way formed over billions of years. In this way, chemistry becomes a kind of time machine, letting us read a star's past like a line of ancient poetry written in light itself. Stellar streams like ghostly ribbons. Across the sky, thin ribbons of stars stretch in graceful arcs and curves. They're barely visible to most telescopes, but unmistakable when mapped with precision instruments. These are stellar streams, the scattered remnants of smaller galaxies that wandered too close to the Milky Way and were pulled completely apart by tidal forces. As these doomed galaxies orbit, their stars get smeared across space, forming long, delicate trails that trace their former paths through the cosmos. Some streams wrap around our galaxy like ghostly halos, others dive inward toward the core. These streams are powerful evidence of past collisions, quiet mergers that built the Milky Way piece by piece over billions of years. The galaxy, like an ancient tree, carries the rings of its past in every thread of scattered starlight. The warped disk. Our galaxy doesn't actually lie perfectly flat like an ideal spiral should. Its disk bends upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warping was completely invisible to us until radio telescopes mapped the hydrogen gas that stretches far beyond the visible starlight. Astronomers believe this distortion may be caused by satellite galaxies tugging gently on the Milky Way's edges, or perhaps by clumps of dark matter bending the structure from below. Like ripples moving through a great spinning sheet, the warp reveals that even galaxies are never fully still or perfectly formed. Over cosmic time, they bend, flex, and change shape in response to invisible forces. From a distance, the Milky Way might actually look like it's dancing slowly through space. The tiny fraction we can see. Under a perfectly clear, dark sky, far away from any cities or streetlights, you might be able to see a few thousand stars with your naked eye. To the human eye, gazing up at that view, it seems like an ocean of light, an overwhelming number of stars. But that's barely a droplet compared to what's really there. The Milky Way contains over 100 billion stars. Most are completely hidden from our view. Some lie behind thick curtains of interstellar dust. Others are simply too faint or too far away for our vision to reach them. That pale streak of the Milky Way that crosses the sky on moonless nights, that's just the innermost whisper of the whole thing. We live surrounded by a truly colossal river of starlight, and yet almost all of it remains invisible to us. It's too vast, too overwhelming to grasp from our position within it. Different speeds, spiral arms. Unlike planets in our solar system, which follow neat, predictable tracks around the Sun, stars in the Milky Way move with much more freedom. Some race ahead quickly in the inner regions near the galactic center. Others drift slowly along the sparse outskirts. This difference in orbital speed is actually why spiral arms form in the first place. Arms aren't solid, permanent structures. They're more like patterns, like slow traffic jams of stars and gas moving through space. As these density waves pass through a region, they trigger the formation of new stars, lighting up the arms in beautiful curls of blue and white light. Our own sun is part of this swirl, moving gradually in and out of these patterns across millions of years. The galaxy isn't a precise clock mechanism. It's more like a current, a flow, and we're all drifting along within it. The invisible scaffolding. By all logical calculations, the Milky Way shouldn't exist, at least not in its current form. Based purely on what we can measure directly, like stars, dust, and gas, the outer edges of the galaxy are spinning far too fast. They should be flung into space, scattered like leaves in a violent storm, and yet, mysteriously, they remain perfectly stable. The answer lies in something called dark matter. This deeply mysterious substance doesn't shine, doesn't reflect light, doesn't emit any radiation we can detect, but it does exert gravitational force. And there's so much of it surrounding and permeating our galaxy that it outweighs all the visible matter many times over. We still don't know what dark matter actually is. It's one of the biggest mysteries in all of physics. But we know beyond doubt that without it, the Milky Way would simply fly apart. Dark matter is the invisible scaffolding holding everything in place. The sleeping giant at the heart. At the very center of the Milky Way, hidden behind thick veils of dust, lies an enormous black hole called Sagittarius A star. It contains more than 4 million times the mass of our Sun, yet it occupies a space smaller than the orbit of Mercury. We cannot see it directly because nothing, not even light, can escape from it. But we've watched nearby stars whip around it at tremendous speeds, tracing invisible loops through the void, their motion revealing the black hole's presence. Sometimes gas and dust fall inward toward it, and just before crossing the point of no return, they flare brilliantly with X-rays as they spiral down into the event horizon. For now, Sagittarius A star sleeps relatively quietly, but long ago it may have burned like a quasar, one of the brightest objects in the universe, lighting up the entire galaxy from within. It's the silent conductor at the Milky Way's heart, pulling stars into a slow, relentless gravitational dance. The peanut-shaped bulge. When astronomers carefully mapped the very center of our galaxy, they discovered something quite unexpected. The central bulge isn't a smooth, round ball of stars like you might imagine. Instead, it's shaped more like a three-dimensional peanut. Seen from the side, it swells noticeably in the middle and narrows at the ends, like a twisting hourglass made entirely of stars. This strange geometry likely formed from the galaxy's central bar, which is a dense stripe of stars that rotates slowly over time, buckling and puffing upward as it does. These complex inner structures are sculpted by gravity, by billions of years of motion, and by the accumulated rhythm of stellar orbits overlapping. We live in what looks from outside like a spiral galaxy, but its heart is full of unexpected complexity. It's not flat or clean or simple. It's intricate and alive with motion. Where stars are born. The Milky Way's spiral arms aren't simply made of stars that happen to be there. They're actually woven from the birthplaces of stars. Giant clouds of hydrogen, dust, and complex molecules drift through the galaxy. And when these clouds pass through the density waves of the spiral arms, they get compressed and squeezed. This compression sets them alight with newborn suns. These regions are called stellar nurseries, and they're chaotic, glowing, and full of violent motion. Intense ultraviolet light from newly formed massive stars lights up the surrounding clouds, painting the spiral arms with radiant blues and silvers. These brilliant bursts of creation trace out the spiral shape clearly, illuminating the curves of the galaxy with what looks like quiet fire. Every star in the sky, including our own sun, was born from one of these cloudy cradles long ago. The vast halo beyond. Beyond the flat spiral disk that we usually picture lies something far more diffuse and mysterious. It's called the galactic halo, a roughly spherical region that completely surrounds the entire galaxy. It contains ancient stars, compact globular clusters, and absolutely enormous amounts of dark matter. Though it's nearly invisible in photographs, this halo may actually hold the majority of the Milky Way's total mass. The stars in the halo are spread incredibly thin across vast distances, orbiting on long, slow arcs that rarely come anywhere near the main disk. The halo also preserves the remnants of ancient galactic mergers, long streams and shells of stars that were torn from smaller galaxies and left behind like cosmic fossils. It's the galaxy's outer memory, quiet and dim, but still in motion, still actively shaping what the Milky Way is becoming. Ancient globular clusters. Globular clusters are among the oldest structures in our entire galaxy. They're compact spheres made of hundreds of thousands of stars, all tightly bound together by gravity. These clusters orbit the galactic center out in the halo, circling like moths around a distant flame. They're incredibly stable structures. Some are more than 12 billion years old, and many contain stars that actually predate the Milky Way itself. Their stars are what astronomers call metal poor, meaning they formed very early, before the universe had time to create many of the heavier elements through stellar processing. These clusters serve as time capsules, holding precious clues about how our galaxy first formed, what it consumed along the way, and what conditions were like in the very early cosmos. These quiet, golden spheres drift patiently above and below the galactic plane, still glowing softly in the dark after all these billions of years. Still growing after all this time. Although the Milky Way is incredibly ancient, it genuinely isn't finished forming, even now at this moment. It continues to gather new material from its surroundings. Gas drifts in from the intergalactic medium. Stars are captured from dwarf galaxies that wander too close. Streams of dark matter flow inward, feeding the halo and adding to the galaxy's total mass. The galaxy grows not like a living organism exactly, but like a gravitational structure that deepens and becomes more complex over time. Some of this growth happens quietly and gradually through the slow infall of gas clouds. Other times, growth comes with real disruption, as entire satellite galaxies are violently torn apart and their stars scattered across the sky in long streams. The galaxy you're living in right now today is not the same galaxy the dinosaurs saw when they looked up, and the Milky Way that your distant descendants might know could be larger still, more complex, stitched together from the ruins of 1,000 smaller worlds. Stars flung into exile. Most stars drift calmly and peacefully through the galaxy on stable orbits that last for billions of years, but a rare few get flung outward at absolutely astonishing speeds, moving fast enough to escape the Milky Way's gravitational pull entirely. These are hypervelocity stars, and they're among the most dramatic stellar exiles we know of. Some are the remnants of binary star systems that were disrupted when they got too close to the supermassive black hole at the galactic center. In these violent encounters, one star of the pair falls inward and vanishes forever beyond the event horizon. The other star gets slingshot outward with incredible force, hurled into the darkness at speeds exceeding 1,000,000 kilometers per hour. These rogue stars travel completely alone, far from the crowded galactic plane, like glowing comets with no hope of return. They remind us that even in a galaxy held firmly together by gravity, there are moments of violent release, quiet expulsions that send stars flying outward into the intergalactic night, never to come home again. The slowing of creation. Long ago, when the Milky Way was much younger, it was far more active, constantly bursting with fresh stars being born from dense, rapidly collapsing clouds. But in more recent cosmic epochs, the pace of star formation has noticeably slowed down. There's still plenty of gas available for making stars, but much of it is now spread too thin, heated too much, or locked in forms that strongly resist gravitational collapse. The galaxy isn't done making stars, not by a long shot, but it is settling into a more mature phase. Astronomers estimate that star formation in the Milky Way peaked several billion years ago and has been gradually declining ever since. This doesn't mean the end is anywhere near. It just means we're living in a quieter chapter of galactic history, watching a mature spiral glowing more gently in its middle age, still forming stars regularly, but no longer in any particular hurry. Stars before the disk existed. The disk, that broad, flat spiral structure we think of as the defining feature of the Milky Way, didn't always exist. It formed gradually over billions of years. But remarkably, some of the stars in our galaxy are actually older than the disk itself. These truly ancient stars reside mostly in the halo, or in what's called the thick disk, and they formed when the galaxy was still assembling itself, when it was just a loose, shapeless cloud of stars, gas and dark matter, slowly collapsing inward under gravity. By carefully studying their chemical composition and their unusual motion patterns, astronomers can peer back into that distant era before there was any structure, before spirals had formed, before there was any galactic order at all. These stars are the elders of our galaxy, silent witnesses to its very birth, to the long, slow process of shaping what we now call home. The long galactic year. As our sun orbits the center of the Milky Way, it completes one full revolution every few 100 million years. This immense cycle is called a galactic year, a vast period of time that absolutely dwarfs all our human calendars and historical records. In the time it takes for the sun to circle the galaxy just once, entire continents drift across Earth's surface, whole species rise and fall, and complete geological epochs unfold and end. Astronomers think we're currently about halfway through one such orbit right now. The last time our solar system was in this particular part of its galactic path, the supercontinent Pangaea had just begun breaking apart, and dinosaurs hadn't even emerged yet. A galactic year is like the slow, deep heartbeat of cosmic time, the rhythm by which galaxies measure their existence. Few trips around the galaxy. In all of its 4.6 billion years of existence, our sun has only circled the Milky Way about 20 times. That's actually far fewer orbits than you might expect, considering the sun's incredible speed of nearly 830,000 kilometers per hour. But the galaxy is simply so unimaginably vast, and the sun's circular path so enormously long, that each complete orbit takes hundreds of millions of years. We often think of stars as ancient and essentially unmoving fixtures in the sky. But on a true galactic scale, our solar system is still relatively young, almost like a newcomer in a city full of much older, more traveled suns. We're part of the galaxy's grand motion and story, certainly, but we're still fairly early in that long, winding tale. Defying Newton's predictions. According to classical Newtonian physics, stars located farther from the galactic center should orbit more slowly, just like outer planets in our solar system move more leisurely around the sun compared to inner planets. It's a basic consequence of gravity weakening with distance, but in the Milky Way, something strange happens. Stars in the outer regions orbit almost as quickly as those much closer to the center. This completely defies those classical expectations. The reason for this puzzling behavior, astronomers now believe, is dark matter. This invisible, still unknown form of mass surrounds the galaxy in an absolutely vast halo, extending far beyond the visible stars. Without dark matter, the galaxy simply wouldn't hold together at all. Its outer regions would fly apart. But with dark matter present, the mathematics works out. The Milky Way rotates more like a solid wheel than it should, not because we fully understand dark matter yet, but because something unseen and powerful is holding everything firmly in place. Enormous molecular clouds. Scattered throughout the Milky Way are vast, dark clouds of extremely cold gas. These are the raw materials from which stars form. These molecular clouds, composed mostly of hydrogen molecules with traces of dust and other compounds, can span hundreds of light years across. Just imagine a cloud of gas larger than the distance between stars, drifting slowly through the galaxy. Within their cold, dense interiors, gravity gradually begins to gather material together, forming clumps that slowly collapse inward to eventually become new stars and planetary systems. Some of these clouds are so incredibly large and so cold that they absorb visible light almost entirely, appearing as jet-black patches against the otherwise starry sky. They're the galaxy's wombs, quiet and hidden places where the entire future begins in silence, tucked safely within curtains of shadow and molecular gas. Supernovae stir the galaxy. When truly massive stars reach the end of their lives, they don't fade quietly. They explode in absolutely cataclysmic events called supernovae, explosions so unimaginably powerful they can briefly outshine entire galaxies. These explosions don't just mark the end of stellar lives, though. They actively create new possibilities. Powerful shock waves from supernovae ripple outward through the interstellar medium, compressing nearby gas clouds and triggering fresh waves of star formation. These explosions also enrich the surrounding space with heavy elements like iron, gold, and platinum, elements that were forged deep in the heart of the dying star and scattered into space. In this way, supernovae act like massive storms within the galactic ecosystem, stirring up the environment, fertilizing it with new elements, and fundamentally reshaping everything around them. They're the galaxy's moments of productive chaos, simultaneously destructive and creative, violent yet absolutely necessary for cosmic evolution. Dust that hides creation. The Milky Way is absolutely full of light we simply cannot see with our eyes. Interstellar dust, made of microscopic grains of carbon, silicon, and ice, weaves through the galaxy in thick clouds and delicate tendrils. In visible light, this dust obscures vast regions of space, completely blotting out background stars and entire nebulae, creating what look like holes in the sky. But behind this obscuring veil, star formation continues vigorously. Infrared telescopes can peer straight through the dust, revealing glittering stellar nurseries absolutely filled with newborn suns. What looks like empty darkness to our eyes is often actually a cradle of creation. The dust, though it hides so much from us, is actually part of the star formation process itself, absorbing and redistributing energy, helping gas cool down enough to collapse, and shielding the delicate early stages of stellar birth. What seems like emptiness is often the very beginning of something extraordinarily bright. Starless clouds waiting. Not every cloud of gas in the galaxy becomes a star. Across the Milky Way, astronomers have found massive, cold molecular clouds that seem perfectly positioned for gravitational collapse, yet somehow remain completely dark and dormant, with no star formation happening inside them at all. Some of these clouds are probably too diffuse, too spread out for gravity to fully take hold. Others may be stabilized by internal magnetic fields or by turbulence within the cloud itself. These starless clouds just float quietly through the galaxy like silent possibilities, rich in molecular hydrogen, but untouched by the fire of nuclear fusion. They may one day ignite with star formation if conditions change, or they may simply drift along until they're torn apart by external forces, their gas eventually recycled into other regions of the galaxy. In these patient clouds, the galaxy seems to hold its breath, waiting perhaps for just the right gravitational nudge to spark something entirely new. The great cycle of matter. Stars are not permanent fixtures in the universe. They live for millions or billions of years, burn through their fuel, and eventually die. And in dying, they return their material back to the galaxy. Supernovae spread heavy elements across vast regions. Red giant stars shed their outer layers in beautiful planetary nebulae. All this enriched material joins the thin interstellar medium, where over time it cools, slowly condenses, and eventually forms brand new stars, new planets, and perhaps new life. Every single atom in your body has actually passed through this grand cycle. Each atom was born inside a star billions of years ago, scattered violently into space when that star died, gathered up again into new structures, and eventually, through an incomprehensibly long chain of events, became part of you. The Milky Way isn't a static stage where things simply happen. It's a great engine of cosmic renewal. It breathes in time with its stars, constantly making, unmaking, and beginning again. Metal pour stars as time capsules. In astronomy, when we talk about metals, we don't just mean iron or gold. We mean any element heavier than helium. The very earliest stars in the universe had almost none of these metals, because they formed before any previous generations of stars had lived, died, and scattered heavy elements into space. Today, astronomers actively seek out what we call metal-poor stars, particularly in the halo of the Milky Way. These faint, ancient stars preserve the chemical conditions of a time long vanished. By carefully analyzing their composition, we can peer into the primordial past, into the period just after the Big Bang, before galaxies had matured, before the Milky Way itself had taken its full shape and structure. They're fossils, but fossils made of light and matter, carrying information across billions of years. Wandering far from home. A star's birthplace doesn't always define its ultimate destiny or final location. Over enormous spans of time, many stars drift far away from their original natal clouds, pushed along by gravitational interactions with other stars, by orbital resonances with the spiral arms, or by the slow, persistent pull of the galaxy's overall structure. Some stars are ejected at surprisingly high speeds, flung clear across the disk or even up into the halo. Others migrate much more gradually, slowly shifting their orbits either inward toward the galactic center or outward toward the edges. Even our own sun isn't where it originally began. It has drifted from its birthplace over its lifetime. Tracing the complex paths of stars through the galaxy reveals a Milky Way that is anything but static or orderly. It's a galaxy truly alive with movement, with exchange, with quiet dislocation happening constantly. Home, for a star, may only ever be temporary. The galactic habitable zone. Just as Earth orbits in what we call the habitable zone around our sun, not too hot and not too cold for liquid water and life, the Milky Way itself may have its own galactic habitable zone. This special region is thought to lie somewhere between the dangerous inner core, which is full of intense radiation and gravitational chaos, and the sparse, metal-poor outer edges, where planets might be much harder to form because of the lack of heavy elements. Somewhere in between these extremes lies a broad band where conditions seem especially favorable. Star density is moderate, so devastating supernova explosions nearby are relatively rare. Elements like carbon, oxygen, and iron are abundant enough to form complex chemistry and rocky planets. Earth sits comfortably within this zone, following one quiet orbit in a vast swirl where life might not be alone in finding a stable foothold. The flowing spiral arms. The Milky Way's beautiful spiral arms might seem like permanent features, grand sweeping structures carved permanently into the galaxy's disk. But they're actually not made of the same fixed stars at all. Instead, they're patterns, what physicists call density waves that ripple slowly through the disk over time, compressing gas and triggering new bursts of star formation as they pass through each region. Individual stars drift into these spiral arms, shine brilliantly there for a while, and then drift back out again on the other side. The spiral structure itself moves at a completely different speed than the stars do, like a traffic jam moving along a highway. The cars change, but the jam persists. From very far away, looking down on the galaxy, it looks like solid form and beautiful order. But from within, from our perspective, it's really a shifting pattern of motion and light, held together by gravity and time, never truly still, always flowing and changing. The galaxy's many voices. Beyond the visible light we can see, the Milky Way glows and hums with far more mysterious and exotic forms of energy. Cosmic rays, which are high-energy particles born in supernova explosions and other violent events, stream constantly through space. They're passing through your body right now, every single second, carrying energy from distant catastrophes. X-rays and gamma rays shimmer from dying stars, from material falling into black holes, and from the hottest regions of space. Radio waves drift outward from vast gas clouds, from rapidly spinning pulsars, and from the cold whisper of hydrogen gas spread throughout the galaxy. These invisible frequencies reveal what ordinary visible light simply cannot show us. They reveal the violence, the powerful magnetism, and the ancient fires still flickering within the galaxy's very bones. When you look up into the night sky with just your eyes, you're only seeing one narrow band of the Milky Way's true spectrum. Beneath those visible stars, the galaxy hums softly in many colors, many frequencies we can't perceive. It's a hidden symphony playing constantly in the dark. Giant gamma ray bubbles. Stretching tens of thousands of light years above and below the galactic center are two absolutely vast, ghostly lobes of high-energy light. They're called the Fermi bubbles, discovered only recently by the Fermi Gamma Ray Space Telescope. They glow intensely in gamma rays, the most energetic form of light, extending like twin balloons inflating upward and downward from the Milky Way's heart. No one is entirely certain what caused these enormous structures. They may be the remnants of a long-ago outburst from our central supermassive black hole, a time when it was actively feeding and releasing tremendous energy. Or they could be the mark of an intense period of star formation that once flared violently through the core. Either way, these colossal structures drift silently over our entire galaxy, completely invisible to human eyes and to most telescopes. They're powerful reminders that the Milky Way has a dramatic past we cannot fully see, echoes of ancient violence wrapped in ghostly radiance, floating far above the familiar stars we know. Our quiet neighborhood. Our solar system doesn't actually lie in one of the Milky Way's grand, prominent spiral arms. Instead, we occupy a smaller structure called the Orion Spur, sometimes called the Orion Arm. It's a relatively minor lane of stars, nestled quietly between the much larger Sagittarius and Perseus arms. It's not an especially dense region, nor particularly active with star formation, but that relative quiet may actually be exactly why we're here at all, why life had a chance to develop. In this calm stretch between the galactic highways, massive supernova explosions are significantly rarer. Dangerous radiation storms are less frequent. Gravitational disturbances from passing stars are less common. From the outside, looking at maps of the galaxy, the major spiral arms seem dramatic and radiant and exciting. But here in this quiet spur, tucked away from the main action, we found just enough peace and stability for the slow, delicate process of biological complexity to gradually unfold over billions of years. The bar-shaped heart. When astronomers look directly toward the galactic core using infrared light, which can penetrate the obscuring dust, they see something interesting. The center isn't a perfect circle or sphere. Instead, there's a thick, elongated bar of stars crossing straight through the middle, like a glowing bridge spanning the inner galaxy. This bar rotates slowly over time, and its powerful gravitational influence actively shapes the inner spiral arms, controlling how they twist and where they begin. Bars like this one are actually quite common in spiral galaxies throughout the universe. They tend to form naturally when stars in the inner disk begin to drift inward and pile up along a central axis, creating a stable, elongated structure. Over time, the bar becomes a persistent feature, stirring up gas, triggering waves of new star formation, and funneling material inward toward the supermassive black hole at the very center. It's not just a static shape in the galaxy. It's a dynamic engine, actively sculpting and reshaping the galaxy's heart from deep within. Part of the local group. The Milky Way doesn't exist in cosmic isolation. It actually belongs to a collection of more than 50 galaxies known as the local group, a small cluster of galaxies all drifting together through space, bound together by their mutual gravity. The two largest members by far are the Milky Way and the Andromeda Galaxy, each surrounded by its own family of smaller satellite galaxies orbiting around it. Scattered around these two giants are numerous smaller dwarf galaxies, faint elliptical galaxies, and even some strange star-poor galaxies made almost entirely of dark matter with barely any visible stars at all. The local group spans more than 10 million light-years from one side to the other. It's bound together not just by physical proximity, but by the invisible threads of gravity. We're genuinely part of a cosmic family, widely spaced across vast distances, but still fundamentally linked by shared motion and mutual gravitational pull. Gravitationally bound together. Despite the truly vast separations between them, the galaxies of the local group are not actually drifting apart from each other. In fact, quite the opposite. Many are moving slowly but steadily toward one another, following the pull of gravity. They're caught in a kind of slow-motion gravitational ballet that plays out over millions and billions of years. Some of the smallest dwarf galaxies orbit the Milky Way almost like moons, looping around us, gradually falling inward, and slowly dissolving into long stellar streams. Other galaxies drift more independently through the local group, but they remain gravitationally tethered, caught in an invisible web of shared motion. Over enormous spans of time, this whole group may gradually condense. Individual galaxies may merge with each other, fade into larger structures, or be completely absorbed. It's not a static arrangement frozen in time. It's a gentle, ongoing process, a slow gathering of cosmic islands, a family being drawn gradually closer together by time, momentum, and the long, patient reach of gravity. The layered disk. The Milky Way's disk might look perfectly flat when you see artistic representations, but up close, when you examine it carefully, it's actually layered into distinct components. There's what astronomers call the thin disk, which is where we live. It's a wide, relatively dense plain filled with young stars, open star clusters, and active star-forming gas clouds. But above and below the thin disk lies something different, called the thick disk. It's older, puffier, more spread out vertically, and more diffuse overall. Stars in the thick disk tend to be significantly older than those in the thin disk, and they have fewer heavy elements in their composition, suggesting they formed under different conditions long ago. These thick disk stars also move in orbits that are noticeably more tilted and elliptical compared to the neat circular paths in the thin disk. This suggests they may have been stirred up by early galactic collisions or formed during a more chaotic period in the galaxy's youth. The galaxy's disk isn't uniform or simple. It has texture, layers, structure shaped by billions of years of history. It's like geological sediment settled gradually on the floor of a vast cosmic ocean. Invisible magnetic threads. Though completely invisible to our eyes, the Milky Way is actually laced throughout with a vast, complex magnetic field. This field stretches across the entire disk, rises up into the halo, and weaves intricate patterns through the interstellar medium. This magnetic field is extremely weak by earthly standards. You'd never feel it or notice it directly, but over the immense distances of galactic space, it has real, measurable effects. It shapes how cosmic rays travel through the galaxy, bending their paths. It influences how gas clouds collapse to form stars. It controls how matter flows through space along invisible magnetic field lines. The galactic magnetic field tends to align roughly with the spiral arms. It forms graceful arcs rising above the galactic plane. It twists into complex loops that scientists are still working to fully map and understand. Studying this magnetic field requires specialized radio telescopes and very careful analysis of subtle signals. But its presence throughout the galaxy is absolutely unmistakable. The Milky Way doesn't just glow with starlight. It breathes with magnetism, a subtle pulse of electromagnetic force running through its fundamental structure. The complex interstellar medium. Between the stars lies far more than simple emptiness or vacuum. The interstellar medium, that thin blend of gas, dust, and plasma, weaves its way through the entire Milky Way like an invisible fog. To the naked eye, most of it is completely invisible. But when astronomers view it with radio telescopes and infrared instruments, it reveals absolutely stunning complexity. The interstellar medium forms delicate filaments stretching between stars. It creates enormous bubbles blown out by stellar winds. It shows shock waves from ancient supernova explosions rippling outward. It reveals cold, dense clouds where new stars are just beginning to form. Supernova explosions carve out vast cavities in this medium, creating huge voids surrounded by compressed shells. Powerful stellar winds sculpted into shapes and structures that ripple and flow across light years of space. The space between stars isn't empty void at all. It's a constantly shifting, dynamic web of matter and energy and magnetism. It's the quiet fabric from which entire galaxies evolve, and from which ultimately life itself begins. Cosmic rays passing through us. Every single second, high-energy particles stream through your body at nearly the speed of light. Most are protons and atomic nuclei that were launched long ago by exploding stars. These are cosmic rays, and they are truly everywhere throughout the galaxy, constantly moving, constantly passing through everything. They travel immense distances, their paths bent and twisted by magnetic fields, bouncing off clouds of gas, occasionally colliding with atoms in Earth's atmosphere, where they create cascading showers of secondary particles raining down to the surface. Most of the time, we don't notice them at all. They pass through us harmlessly, but they carry with them fascinating stories from across the galaxy. They're evidence of ancient supernova explosions. They're traces of distant stellar catastrophes. They're messages from the most violent, energetic parts of stars scattered throughout space. Even as you rest quietly here, drifting towards sleep, the galaxy is constantly whispering to you in particles you cannot feel, in silent streams of energy, in invisible rays carrying the history of cosmic violence. Beautiful asymmetry. Though many textbook diagrams show the Milky Way as a neat, perfectly even spiral, the real galaxy is not perfectly balanced at all. One side of the disk appears noticeably thicker than the other. Some spiral arms are brighter, longer, or more dramatically curved than their counterparts. The warp in the outer disk is distinctly lopsided, bending more on one side. Even the total star counts between different hemispheres of the galaxy are slightly off, not quite matching. These various asymmetries may be caused by past gravitational encounters with other galaxies, by the lingering effects of ancient mergers, or by the uneven distribution of dark matter in and around the galaxy. These imperfections remind us of something important. Galaxies, like living things, carry visible traces of their complex histories in their shapes. They bear scars of ancient collisions. They show wrinkles formed by time. They display quirks of uneven growth that give them real character, real depth, real personality. Perfect symmetry would actually be boring. The asymmetry is what makes our galaxy uniquely itself. Ancient halo stars. High above the galactic plane, drifting slowly through the sparse halo, astronomers have discovered stars that may be nearly as old as the universe itself. Some of these ancient stars contain almost no heavy elements whatsoever. This chemical signature clearly indicates they were born very soon after the Big Bang, long before generations of dying stars had enriched space with carbon, oxygen, iron, and other elements we take for granted. Some of these halo stars likely formed over 13 billion years ago, which means they existed long before the Milky Way was fully formed into the spiral structure we see today. They burn quietly now with soft, reddish glows, low in mass but incredibly rich in history and information. These stars aren't just distant points of light. They're genuine time capsules, living relics from the universe's earliest dawn, from a time when galaxies were just beginning to take shape. When we study their light carefully, we're quite literally seeing echoes of the universe's childhood. The spinning core. In the inner regions of the Milky Way, close to the galactic center, stars orbit incredibly rapidly. Near the core, the gravitational pull is enormously stronger because of all the concentrated mass. Stars, dense clouds of gas, the central bar, and of course the supermassive black hole Sagittarius A star all contribute tremendous gravitational force in that region. This causes stars near the center to sweep through much tighter, much faster orbits, completing full revolutions around the galactic core in just a few million years. That might sound like a long time, but it's remarkably quick on cosmic scales. Out here in the suburbs of the galaxy, like where our sun comfortably lives, stars orbit far more slowly and gently, taking hundreds of millions of years to complete each orbit. This uneven, differential rotation creates interesting twisting patterns throughout the galaxy. It stretches and shapes the spiral arms. It keeps the disk from behaving like one solid, rigid structure. The galaxy moves through space like an enormous wheel, but it's a wheel whose outer rim perpetually lags behind its rapidly spinning core. Density waves shape the arms. The spiral arms of the Milky Way are not fixed, permanent trails of specific stars that stay in the arms forever. They're actually shifting patterns formed by waves of higher density, moving gradually through the entire galactic disk. As gas and dust pass through these density waves, they get compressed by the increased gravitational pull. This compression triggers rapid star formation, lighting up the arms brilliantly with hot, young blue-white stars. But here's the key thing. These bright stars eventually drift out of the density wave that created them, while new stars continue forming behind them in the wave. This creates a beautiful self-sustaining illusion of solid structure. It's very much like ripples spreading across a pond, or like traffic congestion forming on a highway and then slowly moving along while individual cars pass through it. The arms appear stable and permanent when you look at the galaxy from a distance. But from within, from our perspective, they're actually an elegant dance of matter and rhythm and timing, constantly shaped and reshaped by gravity flowing through time. Born from collapsing cold. In the darkest corners and spiral arms of the Milky Way, star formation begins in profound silence and cold. Massive clouds of molecular hydrogen, sometimes hundreds of light years wide, drift slowly through space. These clouds are chilled to just a few degrees above absolute zero, the coldest possible temperature in the universe. Within these incredibly cold clouds, gravity gradually, patiently takes hold. Small regions within the cloud grow slightly denser than their surroundings. These denser regions begin to collapse under their own weight, very slowly at first. As the gas falls inward toward the center, it naturally heats up from compression. It begins to spin faster. It flattens into a rotating disk. Over perhaps 1 million years or so, a protostar forms at the very center of this collapsing region. The pressure and temperature deep inside continue to climb. Eventually, they reach a critical threshold where nuclear fusion suddenly ignites, and a brand new star blazes into existence. From the coldest, darkest shadows of space come the brightest lights imaginable, spun gently and patiently into being by nothing more than the quiet, persistent force of gravity. Dissolving star clusters. Many stars are not born in isolation. They're born in groups, sometimes hundreds or thousands of stars forming together in tight clusters from the same giant collapsing gas cloud. These young clusters are bound together by their mutual gravitational attraction, and they drift through the galaxy together for millions or even billions of years like stellar families. But over enormous spans of time, even these tightly bound clusters begin to slowly scatter and dissolve. Tidal forces from the Milky Way's overall mass gradually pull on them. Close gravitational encounters with other passing stars tug individual members away. Internal dynamics within the cluster itself cause stars to occasionally get ejected. Stars peel away from the cluster one by one, slowly, until eventually the cluster completely fades and merges into the general background starfield of the galaxy, becoming indistinguishable from everything else. Even our own sun was almost certainly born in a stellar cluster like this, long ago, over 4.5 billion years in the past. Its sibling stars are now scattered across the galaxy, dimmed by distance, lost in the overwhelming haze of billions of other suns. Family reunions are impossible when you're separated by thousands of light years. Hypermetal poor relics. Among the rarest and most scientifically precious objects in the entire Milky Way are what astronomers call hypermetal poor stars. These are stars whose outer atmospheres contain almost no elements heavier than helium at all. Some contain less than 1/10,000th the amount of iron found in our sun's atmosphere. These remarkable stars are believed to be among the very first born after the universe's first generation of massive stars exploded as supernovae, scattering just the tiniest traces of heavy elements into space. They carry only the faintest chemical enrichment from a universe still actively forming and learning how to make complex elements. They are incredibly old, often more than 13 billion years. They're incredibly chemically pure compared to younger stars like the Sun, and they're scattered sparsely through the galactic halo like distant lanterns from the cosmic dawn. Each one discovered is treated like a genuine relic, a glowing, gravitationally bound signature from a near-forgotten epoch of universal history, holding secrets about how the first stars lived and died. Planets throughout the galaxy. Planets are not some rare, unusual feature limited to just a few special stars. They're actually a completely natural consequence of normal star formation happening throughout the galaxy. As a new star ignites at the center of a collapsing cloud, a rotating disk of leftover gas and dust surrounds it. This is called a protoplanetary disk. Within this spinning disk, tiny particles naturally stick together when they collide. They gather more and more mass over time. They grow from dust grains to pebbles to boulders to planetesimals to full planets. It happens almost automatically given the right conditions. Across the Milky Way, planetary systems are genuinely common, not rare exceptions. Some systems are vast, dominated by enormous gas giants and populated by frozen moons. Others are compact, with small rocky planets hugging close to dim red dwarf stars. Some may resemble our own solar system quite closely, while others might defy our expectations entirely, with configurations we've never imagined. The galaxy is not just full of stars burning in isolation. It's full of complete systems, solar families, each one with its own unique balance of planets, orbits, and potential. Near the co-rotation radius. In the Milky Way, here's something interesting. The spiral arms rotate at a different speed than individual stars do. The arms are patterns, density waves, not solid structures. But there's a special distance from the galactic center called the co-rotation radius, where the average orbital speed of stars happens to match the rotation speed of the spiral arm pattern itself. Our Sun orbits very close to this special co-rotation boundary. This gentle match in speeds may actually help us avoid frequent crossings through the spiral arms, which are regions of higher star density, more frequent supernova explosions, and more gravitational disturbances that could potentially affect planetary systems. We live, quite possibly, in a more stable neighborhood of the galaxy. We're shielded not by physical walls or barriers, but by a fortunate resonance, a matching of rhythms that keeps us mostly in the quiet spaces between the more active spiral arms. The Sun's gentle oscillation. As it orbits the Milky Way in its long galactic journey, the Sun doesn't follow a perfectly flat, level path through the disk. Instead, it moves in a gentle wave pattern, drifting gradually above and below the midplane of the galactic disk like a cork, bobbing in very slow motion on an ocean. This vertical oscillation happens over tens of millions of years. It's caused by the gravitational tug of the galaxy's mass distribution pulling and releasing the solar system as it travels along. The Sun rises above the plane, slows, stops, then falls back through the plane, continues downward, slows again, and reverses to rise back up. This cycle repeats over and over. Some researchers have even wondered whether this gentle up and down motion might somehow influence long-term cycles of extinction events on Earth, though the evidence for that remains unclear and controversial. Still, it's a fascinating reminder. Even on its steady, reliable path around the galactic center, the Sun isn't simply gliding smoothly. It's swaying softly through three-dimensional space. The mystery of dark matter. Dark matter makes up the vast majority of the Milky Way's total mass, and yet it has never been directly detected or seen by any telescope or instrument ever built. It does not emit any light or radiation. It doesn't absorb light passing through it. It doesn't reflect anything. It passes through ordinary matter as if it essentially weren't there at all. And yet, its gravitational effects are completely unmistakable throughout the galaxy. Dark matter holds the Milky Way together structurally. It explains the unexpected rotation speeds of stars, especially in the outer regions. It shapes the formation and evolution of all large-scale cosmic structures we observe. Without dark matter, the Milky Way would simply fly apart into scattered pieces. Astronomers can detect dark matter's presence not by seeing it directly, but by carefully watching and measuring how it gravitationally moves other things, how it affects visible matter. It is the galaxy's vast hidden scaffolding, invisible, utterly silent, and still one of the very greatest unsolved mysteries in all of science. We know it's there. We can measure its effects precisely, but we genuinely don't know what it actually is. More mass in the halo. Most of the Milky Way's visible, luminous stars lie within the relatively flat, bright disk that we usually picture when we think of the galaxy. But the majority of the galaxy's actual mass resides elsewhere entirely. Our galaxy is completely surrounded by an absolutely enormous dark matter halo extending far, far beyond even the furthest visible stars. This invisible halo holds the entire galaxy together with its gravity, and it outweighs the visible disk by a very large margin. The halo is populated only sparsely with ancient visible stars and globular clusters, but its true bulk, its true mass, is completely unseen dark matter. When we think about the Milky Way, we naturally picture its beautiful spiral arms and its bright starry plane. But that's really only the glowing surface, the visible part. The mass that truly defines the galaxy, that controls its gravity, its motion, its reach through space, is mostly hidden from view, enveloping everything like an enormous quiet shroud we cannot see. The core may have blazed. Today, when we look toward the heart of our galaxy, the central region appears relatively quiet. The supermassive black hole isn't actively consuming huge amounts of matter, but there's strong evidence suggesting it was dramatically different in the past, that it was once far more active and violent. The presence of those huge gamma-ray structures, the Fermi bubbles, combined with traces of ancient high-energy light reflected off surrounding gas clouds, suggests that the black hole at the Milky Way's center may have once flared brilliantly as a quasar billions of years ago. Quasars are among the single brightest objects in the entire universe, powered by matter falling rapidly into supermassive black holes and releasing tremendous energy. A quasar can literally outshine its entire host galaxy, sending radiation across billions of light-years of space. If the Milky Way once burned like this in its youth, it would have looked completely, dramatically different, a spiral wrapped around an absolutely blinding heart of searing light. That violent time has long since passed, but the echoes, the remnants, they remain visible, telling us about a more active past. Constantly changing structure. Galaxies may appear timeless in photographs, like permanent sculptures frozen in space, but they're actually always evolving, always changing, always in motion. Spiral arms gradually shift their positions. Central bars form over time, strengthen, or potentially dissolve. Gas flows steadily inward towards star-forming regions and outward from supernova explosions. Stars are constantly being born from collapsing clouds, and old stars are dying, leaving behind different types of stellar remnants. This changes the overall population and appearance of the galaxy over time. Even the overall shape of the Milky Way's disk, currently warped, rippling slightly and lopsided in places, is slowly changing. Ongoing encounters with dwarf galaxies, interactions with clumps of dark matter, all of these gradually bend or twist the structure. Over billions of years, the galaxy's basic silhouette has shifted and morphed like a drifting cloud slowly changing shape. The Milky Way we see today is genuinely not the same galaxy that existed billions of years ago, and it's not the galaxy that will exist billions of years in the future. Its beauty lies not in permanence or unchanging perfection, but in quiet, ongoing transformation. Gravitational waves passing through. All across the universe, massive cosmic objects collide. Supermassive black holes at galactic centers spiral together and merge. Neutron stars, the collapsed cores of dead massive stars, crash into each other. Entire galaxies merge in slow gravitational embraces. Every one of these dramatic events sends out gravitational waves, actual ripples propagating through the fabric of spacetime itself. Though these waves spread out and become extremely faint with distance, some of them pass directly through the Milky Way, through our solar system, through Earth, and through you. They distort space by absolutely tiny, incredibly subtle amounts as they travel past at the speed of light. These waves are extraordinarily difficult to detect and measure, but observatories like LIGO and Virgo have already successfully captured several clear signals from colliding black holes and neutron stars. New experiments now aim to detect the background hum, the combined gravitational wave signal from countless events throughout cosmic history filling all of space. Even now, as you rest here quietly, space itself is shifting around you, flexing and rippling. Not enough to feel nowhere close, but enough to tell us that somewhere very far away, right at this moment, the universe is dramatically changing, and we can sense its echoes. Stars on tilted paths. Not all stars in the Milky Way move in neat, circular orbits around the galactic center. Some follow long, stretched ellipses instead of circles. Their paths loop high above the disk and plunge far below it, tilted at odd, unusual angles from the main galactic plane. These stars with strange orbits likely come from different origins than normal disk stars. They're often relics of smaller dwarf galaxies that were swallowed and absorbed by the Milky Way long ago, or they're survivors of ancient gravitational upheavals that violently disrupted their original orbits. Their unusual paths are actually valuable clues for astronomers. They act like three-dimensional maps of the galaxy's chaotic past, helping us reconstruct the invisible architecture of the Milky Way's total mass distribution and its long history of mergers. These stars drift through space like messengers from disrupted, destroyed systems. Their orbits tilted and stretched, but still gravitationally bound to the galaxy as a whole. Neutrinos from the galaxy. Every single second, trillions upon trillions of ghostly particles called neutrinos pass straight through your body, coming from the stars. These incredibly tiny particles are produced constantly in nuclear reactions. They pour out from our sun. They're created in supernova explosions. They're generated when cosmic rays strike atoms in space. The entire Milky Way is absolutely bathed in neutrinos constantly. Yet they are so extraordinarily light, so incredibly unreactive with normal matter, that they slip through almost everything, leaving essentially no trace at all. They can pass through entire planets as if the planet weren't even there. Special observatories buried deep underground or placed under Antarctic ice try very hard to catch just a few neutrinos. When a neutrino very rarely collides with an atom, it can produce a tiny flash of light that sensitive detectors can spot. Neutrinos carry unique information from places we cannot observe any other way, from the cores of stars where fusion happens, from the hearts of collapsing supernovae, from the galaxy's unseen sources of energy. They are the whispers of cosmic fire itself, nearly impossible to catch, but always flowing around us. Interstellar turbulence. Between the stars, space is not smooth, calm, or still at all. The interstellar medium, those thin clouds of gas and dust, is actively stirred by shock waves from supernova explosions, by powerful stellar winds, by the motion and rotation of stars, and by complex magnetic fields threading through everything. Temperature throughout the interstellar medium can vary wildly from one region to another. Flows of material collide with each other, mix together chaotically, and fragment into smaller structures. Clouds stretch, fold, tumble, and swirl in complex patterns. On very large scales, all of this creates a kind of turbulence, almost like a slow-motion ocean swirling and churning through the galactic disk. Star formation rates, the paths of cosmic rays, and even the overall evolution of galaxies are all deeply affected by this restless, turbulent sea of gas. What looks from very far away like calm, peaceful starlight is actually, up close, a dynamic, constantly rippling and flowing fabric, shaped by invisible winds, by ancient explosions, and by energy released over billions of years. Rogue planets adrift. Planets are not always permanently tethered to their parent stars. Some planets form normally in young solar systems, but are later violently ejected, flung out into interstellar space by gravitational interactions with other planets or passing stars. Other planets may conceivably never have had a host star at all, forming somehow independently. These are rogue planets, worlds drifting alone through the galaxy, dark, frozen, and utterly isolated. Though they're extremely difficult to detect because they emit almost no light, statistical studies suggest there may actually be billions of them scattered throughout the Milky Way. Some may even drift through the outer halo, where stars themselves are few and far between. Without any sunlight or external warmth, these planets float unseen through the darkness, warmed only by whatever internal heat they still retain from their formation. They are orphans of the galaxy, planetary wanderers following long, lonely paths through the darkness between the stars, forever separated from any sun. Magnetic shaping of dust. Interstellar dust, those tiny grains made of carbon and silicon and ice, moves through space not just under the influence of gravity. It also responds to the galaxy's pervasive magnetic field. These magnetic fields thread through the Milky Way like invisible currents, guiding the motion of electrically charged particles and influencing how gas and dust align with field lines. In some regions, dust grains spin rapidly, emitting very faint microwave radiation. In other regions, the grains align themselves with local magnetic field lines, which causes them to polarize the starlight that passes through them. This effect is measurable with sensitive instruments. Understanding these magnetic effects helps astronomers trace and map the structure of the galaxy's magnetic field throughout different regions. It even helps remove unwanted magnetic foreground signals when studying the cosmic microwave background from the early universe. Interstellar dust isn't just passive debris floating randomly. It actually dances to a magnetic rhythm, falling into hidden patterns in the darkness, responding to forces we cannot directly see. Elements from neutron star mergers. When two neutron stars, the incredibly dense collapsed cores of dead massive stars, spiral together over millions of years and finally collide, they create one of the most violent, energetic events in the entire universe. This explosion is called a kilonova. In this brief, absolutely blinding explosion, enormous quantities of the heaviest elements are forged through rapid nuclear processes. Gold, platinum, uranium, and many other heavy metals are created in these catastrophic collisions and then blasted outward into space. This enriched material eventually mixes with surrounding interstellar gas. Over time, it gets incorporated into new star-forming regions. Some stars in the Milky Way today carry clear chemical fingerprints of these rare, violent events, enriched in specific heavy elements that could only have come from neutron star collisions. These stars aren't just luminous balls of gas. They're record keepers, burning archives of ancient cataclysms, carrying within their atmospheres the residue of stellar wreckage and cosmic alchemy from billions of years ago. A hidden inner bar. At the heart of the galaxy lies that prominent bar of stars we mentioned earlier, an elongated bridge of light crossing the central bulge. But deep within that bar itself, astronomers have found tantalizing hints of something even more complex. There may be another, smaller bar nested inside, tilted at a completely different angle, rotating independently at its own pace. This inner structure is incredibly difficult to observe directly because it's so deeply obscured by layers of dust and because of the sheer distance. But its gravitational influence appears clearly in the detailed motion of nearby stars and in the flow patterns of gas in the central regions. Nested bars like this may help funnel material even more efficiently toward the central supermassive black hole, feeding it and dramatically shaping the dynamics of the innermost core. The Milky Way's center isn't one simple, straightforward shape at all. It's a complex, layered, shifting labyrinth of gravitating light and hidden motion. Fed by the cosmic web, the Milky Way is not a completely closed, isolated system cut off from the rest of the universe. It actively draws in fresh gas from the surrounding intergalactic medium, those long, tenuous streams flowing through the vast cosmic web that connects all galaxies. These steady inflows provide crucial raw material for ongoing star formation, replenishing what the galaxy loses over time through star death, supernova explosions, and gas being heated and expelled. Some gas arrives as cold filaments, slipping quietly into the disk without much fanfare. Other streams fall inward in hotter, shock-heated forms, actually lighting up in ultraviolet or X-ray wavelengths. These invisible rivers of inflowing gas sustain the galaxy's continued growth and evolution, linking it intimately to the larger universe beyond its visible boundaries. Even now, at this moment, the Milky Way drinks slowly from distant cosmic reservoirs, nourished by threads of primordial matter spun from the structure of the early universe. Chimneys through the disk. When large clusters of massive, short-lived stars all explode as supernovae in the same general region over a relatively short time period, they create absolutely enormous cavities in the interstellar medium. These individual bubbles can actually join together to form what astronomers call superbubbles, vast pockets of extremely hot gas. These superbubbles can punch completely upward through the galactic disk and vent their energy and material out into the halo above and below. The result is like a chimney or a channel, a clear path where energy, hot gas, and magnetic fields escape from the confined plane of the galaxy. These chimneys play an important role in regulating the pressure of the interstellar medium. They redistribute heavy elements created in stars throughout a larger volume. They help shape the structure of the galactic halo. In this way, the galaxy doesn't just exist and evolve within its flat disk. It breathes through towering columns of hot gas that carry its energy and matter up and outward into the surrounding dark halo. The X-ray sky. Though the Milky Way appears generally calm and peaceful in visible light photographs, it actually glows quite fiercely in other wavelengths we cannot see with our eyes. X-rays, high-energy light, pour constantly from the galactic core, from collapsed stellar remnants like white dwarfs and neutron stars, and from the immediate surroundings of black holes. White dwarfs and neutron stars in binary systems can actually siphon gas and material directly from their companion stars, heating this stolen matter to millions of degrees and causing it to emit intense X-rays. Hot gas distributed throughout the halo also emits fainter X-ray light, revealing the galaxy's larger skeletal structure. We cannot see any of this high-energy light with our human eyes. It's completely invisible to us naturally, but X-ray space telescopes like Chandra and XMM Newton paint a very different portrait of our galaxy. Not a tranquil, peaceful spiral at all, but a realm of extreme temperatures, compact stellar remnants, and hidden radiation flowing constantly through space. Pulsars as cosmic clocks. When a truly massive star dies and its core collapses inward, it may be left as an incredibly dense neutron star. Some of these neutron stars spin extraordinarily fast, sometimes hundreds of times per second, with powerful beams of radiation sweeping across space from their magnetic poles like a lighthouse beam. These are pulsars, and their rotation is so consistent, so precise, that astronomers actually use them as cosmic timekeepers. Some pulsars are so stable that they rival the best atomic clocks humans have ever built. Their signals can be tracked and measured to incredible precision. Scientists use pulsar timing to measure vast distances across the galaxy, to test fundamental theories of gravity in extreme conditions, and even to search for gravitational waves rippling through space by detecting tiny changes in pulsar pulse arrival times. Across the Milky Way, pulsars blink quietly and steadily, remnants of stellar death, but also beacons of astonishing order and regularity. They keep time not for minutes or hours or days, but for entire epochs of cosmic history, ticking steadily in the profound silence between stars. Radio eyes see through dust. Much of the Milky Way is completely invisible in ordinary visible light, hidden behind thick veils of interstellar dust, obscured by sheer distance, or simply too faint for optical telescopes to detect. But radio waves, much longer wavelength light, can slip easily through these barriers, revealing structures that would otherwise remain completely hidden. Radio telescopes trace cold hydrogen gas spread throughout the galaxy. They outline complex magnetic field structures. They highlight emissions from pulsars, from supernova remnants still glowing with energy, and even from distant quasars shining from far beyond our galaxy. Using large arrays of radio telescopes working together, astronomers have successfully mapped the spiral arms with much better clarity, measured the subtle warp of the galactic disk, and discovered active star-forming regions completely cloaked in darkness to visible light telescopes. Where normal light is completely blocked, radio waves let us see through. The galaxy speaks constantly in wavelengths and frequencies we cannot hear naturally, but that science has learned to translate into detailed maps of shape, structure, and shadow. The Sun's lost siblings. Stars very rarely form in complete solitude. They're usually born in groups, in stellar clusters shaped from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of many stars born together in a cluster. Long ago, perhaps 4.5 billion years in the past, it shared space with hundreds, maybe even thousands of sibling stars, all formed together in the same stellar nursery. Over time, gravitational tides from the Milky Way's mass, chance encounters with other passing stars, and the natural dynamics of the galaxy scattered that birth cluster completely. Most of the Sun's siblings have wandered far away by now, flung into wildly different orbits across the galaxy, carrying with them fragments of our shared origin story. Some of those sibling stars may still shine relatively nearby in our night sky, invisible among the overwhelming number of other stars, lost family members in a vast sea of light. We may never know which stars they are. Searching for solar siblings. Though the Sun's original birth cluster dissolved billions of years ago, astronomers are actively searching for its lost siblings, stars that might share the Sun's age, its overall motion through the galaxy, and most importantly, its detailed chemical fingerprint. Using vast star catalogues from surveys like the Gaia mission, which has precisely measured over 1 billion stars, and combining that with detailed spectroscopic data showing chemical compositions, researchers hope to identify these long-lost relatives of our Sun. A few candidate stars have already emerged from these searches, stars that may genuinely have shared our origin, formed from the same enriched cloud of gas that gave birth to our solar system. If confirmed, they could reveal fascinating details about the specific conditions and environment in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary after all. Somewhere out there among the hundreds of billions of stars, the Sun's ancient kin may still shine, carrying the same cosmic heritage across the light years. The wobbling disk. The Milky Way's disk is not perfectly flat and level. It wobbles gently, rippling like a spinning plate that's been nudged slightly off balance. This warping effect is most clearly visible in the outer regions of the disk, where it bends noticeably upward on one side and curves downward on the other. This warp may be caused by the gravitational influence of nearby satellite galaxies, like the Magellanic Clouds tugging on the Milky Way's edges, or perhaps by interactions with clumps and streams of dark matter, or by internal asymmetries in the galaxy's mass distribution. The wobble itself rotates slowly over time, like a vast wave moving gradually through the stars. From Earth, embedded within the disk, we don't feel this motion at all. But from far away, from an external perspective, the Milky Way is not a pristine, perfect spiral lying in one neat plane. It's a living, breathing, gently undulating sheet of stars, curving and flexing as it turns through space. Tidal forces stretch and pull. Just as the moon's gravity creates ocean tides on Earth by pulling more strongly on the near side than the far side, the immense mass of the Milky Way itself exerts similar tidal forces on everything within its gravitational influence. Star clusters, satellite galaxies orbiting around us, even individual globular clusters, all feel the galaxy's uneven gravitational pull across their structures. Over time, measured in millions and billions of years, these persistent tidal forces can stretch and distort these objects significantly. They draw out long stellar streams, like taffy being pulled. They peel individual stars away from their parent clusters and galaxies, stealing them one by one. Many of the faint arcs and streams of stars that astronomers have carefully mapped across the sky are remnants of exactly such encounters. Their clusters currently in the process of being slowly unraveled, or their galaxies being gradually torn apart over cosmic time. The galaxy doesn't break these structures suddenly or violently. It unravels them with patience, strand by delicate strand, over millions upon millions of years. Uncertain mass. You might reasonably think we would know the total mass of our own galaxy quite precisely by now, but measuring it accurately is actually remarkably difficult. Visible stars, glowing gas and dust make up only a fairly small portion of the galaxy's total mass. The vast majority lies in the enormous dark matter halo surrounding everything, and dark matter cannot be observed directly at all. Current estimates of the Milky Way's total mass vary quite significantly. Some studies suggest a total mass close to 1 trillion times the mass of our Sun. Other analyses, using different methods and data, place it substantially higher, perhaps even twice that much. The uncertainty comes from the challenge of trying to measure how fast stars and gas clouds orbit at extremely large distances from the galactic center, a task made difficult by limited data, large uncertainties in measurements, and the overwhelming influence of invisible dark matter dominating the outer regions. The Milky Way is our home, the galaxy we live within and study constantly. And yet its total weight, its actual mass, remains a quiet and somewhat embarrassing mystery. Perhaps heavier than Andromeda. For many years, astronomers generally assumed that the Andromeda Galaxy, which appears slightly larger and somewhat brighter than the Milky Way when viewed from Earth, was also more massive than our galaxy. It seemed like the biggest sibling in our local cosmic family. But more recent measurements and analysis suggest that assumption might be wrong. The Milky Way's dark matter halo may actually be broader and denser than Andromeda's when you account for everything. If that's true, our galaxy could genuinely outweigh Andromeda despite its slightly more modest visible appearance. This question actually matters quite a bit, not just for comparisons, but for predictions about the future. When the two galaxies eventually merge together in about 4.5 billion years, their relative masses will significantly shape the dynamics of that encounter, determining which galaxy dominates and how the merger unfolds. The Milky Way may look gentle and understated in photographs, but beneath its quiet spiral arms and peaceful appearance, it may actually carry more gravitational weight than we once imagined. The Magellanic Clouds first pass. The Large and Small Magellanic Clouds, those two bright, beautiful satellite galaxies clearly visible from the southern hemisphere, have long been thought to be stable, long-term companions orbiting the Milky Way for billions of years. But fascinating new evidence suggests they may actually be newcomers, captured only recently in cosmic terms. Their measured velocity through space and their unusual motion suggest that this could actually be their first close passage near the Milky Way, not one of many orbits. If that's true, they're not ancient, long-standing companions at all. They're distant wanderers only just now falling under our galaxy's powerful gravitational pull for the first time. Their relatively recent arrival has already stirred and warped the outer disk noticeably, as if the Milky Way is responding and adjusting to a new gravitational guest entering its space. The night sky we see, quiet and seemingly eternal, is actually full of ongoing first encounters, of galaxies meeting for the first time. The Magellanic Stream. Trailing far behind the Magellanic Clouds as they orbit and fall toward the Milky Way, is an absolutely vast ribbon of hydrogen gas stretching across hundreds of thousands of light-years of space. This is called the Magellanic Stream, one of the largest structures associated with our galaxy. This enormous stream of gas was gravitationally pulled away and stripped from the dwarf galaxies as they passed close to each other and to the Milky Way over millions of years. Tidal forces stretched the gas out into this long, graceful arc. Invisible in ordinary light, the stream reveals itself beautifully in radio wavelengths, appearing as a long, trailing whisper of motion and loss, a record of gravitational interaction written across the southern sky. This stolen gas may eventually, over vast timescales, fall into the Milky Way's disk and feed new episodes of star formation. Or it may settle into the halo, becoming another faint thread of memory, a bridge stretching between galaxies and across cosmic time. Polar orbits in the galaxy. Not everything in the Milky Way obediently follows the neat plane of the disk. Some clouds of gas, and even some individual stars, move in highly inclined orbits, passing high above the disk and plunging deep below it, rather than circling within it. These unusual polar orbits likely originated from past mergers, when dwarf galaxies or stray gas clouds were captured at odd, tilted angles rather than merging smoothly into the disk. Over billions of years, These objects have continued to orbit faithfully on their tilted paths, like comets orbiting at extreme angles around a planet. These misaligned orbits are permanent records of disruption and chaos. They're visible reminders that the galaxy is not a perfectly closed, orderly system, but an evolving, dynamic structure constantly shaped by unpredictable encounters and the messy flow of cosmic history. Shells from ancient starbursts. In several regions of the Milky Way, astronomers have discovered enormous spherical shells of gas, some spanning hundreds of light years in diameter. These dramatic structures are the remnants of intense starbursts, relatively brief episodes when large clusters of massive stars all formed together, lived their short lives, and then exploded in rapid succession as supernovae. Their combined powerful stellar winds and violent supernova explosions carved out huge cavities in the surrounding interstellar medium, blowing gas outward in all directions like cosmic bubbles being inflated. Over time, the expansion of these shells gradually slows as they push against surrounding material, but the shells themselves remain visible for millions of years. They're ghostly bubbles in space, marking places where the galaxy once burned extraordinarily bright with concentrated stellar birth and death, episodes of intense activity now long past, but still echoing faintly in the cold gas. Rare stellar collisions. Space is incredibly vast, and stars are relatively small, so direct collisions between stars are extraordinarily rare throughout most of the galaxy. But in the very densest regions, such as the compact cores of globular clusters, where hundreds of thousands of stars are packed into a small volume, stars can occasionally pass close enough to actually interact gravitationally or even physically collide. When this happens, the results can be dramatic and strange. Sometimes there's a burst of light and energy as the stars merge. Sometimes the collision produces what's called a blue straggler star, a star that appears mysteriously younger and bluer than it should be given the age of its cluster, because it gained fresh fuel from the merger. These collisions are rare events, but not impossible. Over billions of years, the tightest, most crowded stellar neighborhoods can slowly rearrange themselves through gravity, close encounters, and occasional chance collisions. In these dense stellar cities, time moves differently than in the sparse suburbs where our sun lives, and space is never quite empty. Binary stars torn apart. Many stars don't live alone. They exist in binary pairs, two stars orbiting each other in a gravitational dance that can last for billions of years. But even this close bond can be violently broken under extreme circumstances. If a binary system passes too close to the Milky Way's central supermassive black hole, or travels through an extremely dense star cluster, powerful tidal forces can disrupt their shared orbit completely. One star might be captured or slowed dramatically, while its companion is flung away at high speed. In some dramatic cases, one companion falls into the black hole and vanishes forever beyond the event horizon. The other star gets hurled outward with tremendous velocity, becoming a hypervelocity star speeding out of the galaxy entirely. These stellar breakups happen silently, invisibly, in distant places we rarely observe directly. They're quiet tearings of ancient partnerships, bonds severed suddenly by gravity's indifferent hand after billions of years together. Escaping the galaxy forever. Most stars are gravitationally bound to the Milky Way for their entire lifetimes, orbiting the center over and over for billions of years. But occasionally, rarely, a star reaches escape velocity, moving faster than about 500 kilometers per second relative to the galaxy, and is flung outward hard enough to escape the Milky Way's gravitational pull forever. These hypervelocity stars are uncommon, but they're real. Some are thought to be ejected by close interactions with the supermassive black hole at the galactic center, where extreme gravitational forces can accelerate objects to incredible speeds. Others may be slingshot outward by three-body gravitational encounters or by supernova explosions in binary star systems. Once free of the galaxy's grip, they travel completely alone into intergalactic space, becoming tiny isolated lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward with them, becoming solitary pilgrims in the great darkness between galaxies, never to return home. Stars from other galaxies. Not every star we see within the Milky Way's boundaries was actually born here in our galaxy. Some may have originated in completely different galaxies, captured and absorbed during ancient mergers, or even flung into our halo from distant regions of the local group. These intergalactic wanderers often move on very unusual orbits, far from the main disk, tracing strange paths through the outskirts or halo. They can sometimes be identified by their distinctive chemical composition or by their motion, which doesn't quite fit the expected local patterns. Like cosmic immigrants, they bring stories from other environments, from other galactic histories, from skies that once looked completely different. The Milky Way is not a sealed, isolated system at all. It's a living mosaic, a patchwork slowly stitched together over billions of years by time, motion, and the patient gathering of material from across the cosmos. The galactic fountain. Above and below the Milky Way's bright, active disk, gas rises and falls in a slow, perpetual loop known as the galactic fountain. Supernova explosions and powerful stellar winds heat gas and eject it upward out of the disk into the halo, where the gas gradually cools over millions of years. This cooled gas then condenses and slowly rains back down onto the disk, pulled by gravity, where it can participate in new rounds of star formation. This cycle stirs and mixes the interstellar medium, redistributes heavy elements created in stars throughout a larger volume, and helps regulate the overall rate of star formation in the galaxy. It's like a quiet respiration, a breathing motion of matter cycling between the dense, active plane and the vast, sparse halo above and below. The galaxy doesn't just spin in place, it circulates material. It exhales and inhales continuously, keeping its structure dynamic and alive across immense spans of time. Organic molecules in dust. Within the clouds of interstellar dust drifting between stars throughout the galaxy, scientists have detected surprisingly complex organic molecules. These are carbon-based compounds, the same basic chemistry that forms the foundation of all life on Earth. These molecules include things like polycyclic aromatic hydrocarbons, simple sugar molecules, various alcohols, and many other organic compounds. Though certainly not alive themselves, they're chemically rich and complex, formed either in the atmospheres of dying red giant stars or within cold clouds shaped by starlight and radiation. These tiny dust grains, carrying their cargo of organic molecules, are transporting across vast distances by galactic winds and supernova shock waves. They settle into the gas clouds that eventually collapse to form new stars and planets. Some of these organic molecules may have actually fallen onto the early Earth, delivered by comets and asteroids. The galaxy's dust is not just debris or waste. It's a cargo ship carrying potential, drifting silently through the darkness with the chemical ingredients that life might someday use. Seeding solar systems with life's ingredients. The birthplaces of stars are simultaneously the birthplaces of entire planetary systems. As these systems form from collapsing clouds of gas and dust, they naturally inherit the specific chemical fingerprints of their parent nebula, the cloud from which they condensed. If that original cloud happens to contain significant amounts of water molecules, carbon compounds, and other organic building blocks of biology, those crucial ingredients may end up incorporated into comets, into asteroids, and onto the surfaces of newly forming planets. Some regions of the Milky Way appear to be especially rich in exactly this kind of prebiotic chemistry. The chemical ingredients that might eventually lead to life. We don't yet know how common life actually is throughout the galaxy, but the basic conditions for it, the raw materials, seem to arise quite naturally and appear to be scattered far and wide. The seeds of life, or at least its chemical precursors, may be scattered throughout the galaxy, tucked into the coldest stellar nurseries, just waiting for the right planet, the right conditions, the right place to grow and flourish. Rapid stellar rotation. Most stars spin at moderate rates, but some spin incredibly, almost unbelievably fast. These rapid rotators, often young and massive stars, can complete a full rotation in just a few hours. That's hundreds of times faster than our Sun, which takes about 25 to 35 days to rotate once, depending on latitude. These extremely fast spinning stars bulge noticeably at their equators from centrifugal force, becoming distinctly flattened rather than spherical. A few reach such astonishingly high rotation speeds that they actually fling material off their surfaces, forming glowing disks of gas around themselves. Their internal structures are different from slow rotators. Their evolutionary paths through stellar life are altered by the rotation. Their lives may be brief and violent, but while they last, they spin like cosmic sirens, blazing bright and rotating at almost unimaginable speeds in the darkness. Tilted relative to our solar system. From Earth, when we look up, the Milky Way arcs across the night sky in a beautiful, graceful band of light. But it doesn't align neatly with the plane of our own solar system at all. The galactic plane, the flat disk containing most of the galaxy's stars, is tilted about 60 degrees relative to the ecliptic, which is the plane traced by Earth's orbit and the other planets around the Sun. This significant tilt is why the Milky Way rises at an angle in the sky rather than following the path of the planets. It's also why the Milky Way's position and orientation shifts noticeably with the seasons as Earth orbits the Sun and our viewing angle changes. We are part of the galaxy, certainly members of its vast stellar community, but our own little planetary system is angled noticeably askew, like a small tilted boat drifting through a much larger spinning sea of stars, following its own slightly different orientation through space. Ancient white dwarfs in the halo. Among the faint, ancient stars scattered through the galactic halo, astronomers have found white dwarfs, the slowly cooling collapsed cores of stars that died billions of years ago. Some of these white dwarfs are genuinely older than the Milky Way's thin disk itself. These ancient stellar remnants formed when the galaxy was extremely young, before its main disk structure had fully settled and organized. Their mere existence hints at an even earlier period of star formation, a deeper layer of history etched into the sparse outer halo. They have been burning and cooling for billions upon billions of years, very slowly fading, carrying with them the quiet residue of a time when the galaxy was fundamentally different, still gathering its shape and structure. The disk we live in may be bright and active, but the halo remembers much further back, preserving remnants from the galaxy's earliest youth. Stars in the distant halo. The Milky Way's most distant stars orbit incredibly far beyond the familiar, well-lit spiral arms we usually picture. They're located tens of thousands, sometimes even hundreds of thousands of light years from the galactic center, moving through the sparse outer halo on extremely slow, wide orbital paths. These remote stars take billions of years to complete just a single orbit around the galaxy. Many were likely captured from smaller satellite galaxies during ancient mergers, now drifting in the outermost reaches of the Milky Way's gravitational influence like distant sentinels standing watch. They are faint, sparse, and separated by enormous distances, but they help astronomers define the galaxy's true size, its overall shape, and the extent of its gravitational influence reaching out into space. The Milky Way is not just what we see clearly in the night sky. It extends deep into the surrounding darkness, shaped and defined by lonely wanderers at its very edge. Lopsided in several ways. Though often pictured in textbooks and planetarium shows as a beautifully symmetric spiral, the real Milky Way is actually subtly lopsided in multiple ways. One side of the disk is measurably thicker than the other. The spiral arms are clearly uneven in their brightness and in how far they extend. Even the stellar halo surrounding everything is slightly off-center from the disk. These various asymmetries likely arise from ongoing gravitational interactions with the Magellanic Clouds, from encounters with clumps of dark matter passing through, or from the lingering structural effects of past galactic mergers that haven't fully settled yet. The galaxy is not a perfect, balanced pinwheel shape at all. It's a living structure marked by gravitational tugs and twists and pulls, like a spinning dancer whose flowing skirt has been caught by an invisible wind. Its beauty lies partly in that subtle irregularity, that graceful imbalance sculpted gradually by billions of years and countless interactions. Variable stars as measuring sticks. Certain types of stars pulse in brightness over regular, predictable intervals, physically expanding and contracting like slow, luminous heartbeats. These are called variable stars, and some specific types, like Cepheid variables and RR Lyrae stars, have very well-known, reliable relationships between their pulsation period and their true luminosity. By carefully measuring how long a variable star takes to brighten and dim through a complete cycle, astronomers can determine its actual, intrinsic brightness. By comparing that true brightness to how bright the star appears from Earth, they can calculate its distance with good accuracy. These special stars serve as cosmic yardsticks, helping us map the three-dimensional shape, structure, and scale of the Milky Way with increasing precision. They're like regularly blinking beacons scattered throughout the spiral, measuring lights in the darkness. The Gaia Revolution. Launched by the European Space Agency, the Gaia spacecraft is quietly creating the most detailed, precise map of the Milky Way ever made in human history. By measuring the exact positions, proper motions, and brightness of more than 2 billion individual stars, Gaia is revealing the galaxy's three-dimensional structure and its motion through time with absolutely unprecedented detail. Gaia has uncovered previously unknown streams of stars from ancient shredded galaxies. It has mapped the subtle warp of the galactic disk with exquisite precision. It has traced the sun's orbit and motion through the galaxy in extraordinary detail. With each new data release every few years, Gaia continues to deepen and revolutionize our understanding of our home galaxy. It's astronomy's most ambitious star chart, the most comprehensive census of the Milky Way ever attempted. It's a quiet revolution unfolding among the stars, transforming our fuzzy, uncertain picture into a sharp, detailed living map. The galactic plane. If you go outside on a perfectly clear, dark night, far away from any cities and streetlights, you may be able to see a hazy, luminous river of starlight stretching across the sky from horizon to horizon. That beautiful band is the galactic plane, the thickest slice through the Milky Way's disk, the direction where you're looking along the plane rather than above or below it. It's not a thin line, it's a band with real depth. It's a vast, flattened region where the overwhelming majority of the galaxy's visible stars actually reside, where dust lanes are thickest, and where star formation is most active and common. Through this dense plane, stars are packed far more closely together than in other directions. From our vantage point embedded within it, we're looking along the grain of the galaxy, peering through its richest, most crowded stellar corridors. This luminous band isn't just beautiful. It's the crowded, humming heart of where most stars in the galaxy live, shine, and eventually die. Brightest toward the center. The core of the Milky Way lies in the direction of the constellation Sagittarius, visible in the summer sky from the northern hemisphere. It's a rich, glowing concentration of countless stars, clouds of gas and dust, and tremendous unseen mass all packed together. From Earth, we cannot see the very center directly in visible light because thick layers of intervening dust completely obscure our view. But the whole region glows noticeably brighter than other parts of the Milky Way, even in visible light. And in infrared and radio wavelengths, which penetrate the dust, the area blazes intensely. Even with just the naked eye on a dark night, that region of sky appears more crowded, more luminous, densely filled with the overlapping light of billions upon billions of stars concentrated toward the core. We orbit far from this crowded center, out here in a quiet suburban region of the galactic disk, about 26,000 light-years away. But when we look inward toward Sagittarius, we're glimpsing the bustling city at the galaxy's heart, the bright core around which everything orbits. Seeing from the inside. Because we live within the Milky Way, embedded deep inside its structure, we cannot look down on it from above to see its full spiral shape clearly. Instead, we see it from the inside, edge on, as a relatively flat ribbon of stars stretching across our sky, curved only by the horizon. This internal, edge-on view compresses the entire three-dimensional galaxy into what looks like a single glowing arc, making it extremely hard to grasp its full structure just from our earthly perspective. It's like standing in a dense forest and trying to map the forest's overall shape by looking along the line of the trees. You see depth, you see individual trees, but the forest's overall form remains hidden. It took centuries of careful observation, patient cataloging of stars, mathematical deduction, and eventually modern technology to finally realize and confirm the spiral shape we belong to. From Earth, we can't directly see the elegant form we're part of, only the vastness that continuously surrounds us on all sides. More than we can see. Even with our most sensitive instruments, our most powerful telescopes, we glimpse only a fraction of what the Milky Way actually contains. Light from countless regions is blocked entirely by dust. Motion and activity happen in silence beyond our ability to detect. Dark matter, making up most of the mass, outnumbers luminous stars by an enormous factor and remains completely invisible. Between every visible star lies vast emptiness, and within every apparently empty space lies potential, dark matter, faint gas, drifting dust, perhaps rogue planets, all the hidden components of a living galaxy. The Milky Way is not just what we see, measure, and photograph. It's also what we suspect must be there, what we infer from indirect evidence, what we long to understand but cannot yet fully grasp. It holds ancient light traveling for thousands of years to reach us, future stars waiting to be born, drifting worlds we may never find, and deep questions still waiting for answers. And within that almost incomprehensible vastness, somehow, remarkably, we find ourselves. One small planet among countless worlds, orbiting a quiet, ordinary star, floating through a story too vast and too beautiful for any eye to fully encompass. Drifting towards sleep. And now the stars begin to dim gently behind your thoughts, fading as sleep draws closer. We've drifted together through so many quiet truths about our home galaxy tonight, from the subtle warp of the disk to the most distant halo stars, from newborn suns igniting in stellar nurseries to ancient remnants slowly cooling after billions of years, from swirling dust and gas to brilliant light and deep shadow and everything existing between. You've wandered through stellar nurseries where stars are born. You've danced along spiral arms shaped by density waves. You've gazed toward the galactic heart glowing behind thick curtains of obscuring dust. You've learned about hypervelocity stars racing away into the void, about dark matter holding everything together, about the slow collision coming with Andromeda billions of years from now. You are genuinely a part of this galaxy, not just a passenger on Earth watching from a distance, but an actual participant in its long, luminous unfolding story. The iron flowing through your blood right now was forged inside stars that died long ago. The oxygen you breathe with every breath was created and scattered by ancient stellar explosions. The very atoms making up your body trace their origins to the earliest times, born from the same primordial matter that now fuels distant suns and whispers through vast clouds of interstellar dust. Tonight, as you rest and drift into dreams, the galaxy continues turning steadily on. Stars are forming in cold clouds. Light is traveling across vast distances. Silent orbits continue their eternal paths, and you are floating peacefully within it all, a small island of warmth and consciousness in the darkness, resting comfortably in the spiral arm of a quiet, radiant sea of stars. If you happen to still be awake, listening to these words, you can go ahead and continue to the next video if you'd like. I genuinely hope you sleep well tonight and dream softly and peacefully. Good night, traveler. Rest well among the stars.